So now we're going to formally look at what we did informally at the beginning, which was curve sketching. And the first formal thing we're going to look at is the first derivative test, which tells us where maximums and minimums can happen. Okay? So, let C be a critical number. Critical numbers are where either the derivative is 0 or the derivative doesn't exist. Those are two possibilities on a function that is continuous. So we could have a continuous function with a derivative that doesn't exist with a corner or a cusp, or we could have it nice, smooth, and differentiable all the way through. If f prime of x changes from negative to positive, and I'm going to draw my sign diagram right now here. I'm going to put f prime of x. I'm going to put some point c. If it changes from negative to positive, negative tells us our graph is decreasing. Positive tells us our graph is increasing. So is C going to be a minimum or a maximum? The sign diagram tells us quite easily it would have to be a minimum. And if we switched from positive to negative, so if I had that same sign diagram for f prime of x at some point C, and it changed, it was positive first and then negative afterwards. Well, negative means decreasing, positive means increasing. And the beautiful thing about making your sign diagram is it's very hard to screw up if it's going to be a minimum or a maximum. Question?
Should a minimum or maximum be like both absolute and relative? Like I know that relative wouldn't exactly mean absolute, but would absolute mean relative also?
Yes, absolute would mean relative also. So if it's the biggest, like on a parabola that opens up, you have a minimum point at the vertex. And that minimum is absolutely the smallest point because it's a parabola. But if you look just around that minimum, it would also be a relative one. Because you're the smallest in your little town and you just happen to find out you're the smallest everywhere. If f prime of x does not change sign at C, so here we go. We've got f prime of x. We have some point C that's a critical number, and it doesn't change sign, so it could stay positive. Well, that would mean it stays increasing. Then it's not going to be a maximum or a minimum. So the first derivative test says, if it changes from negative to positive, obvious that it's a minimum. If it changes from positive to negative, obvious that it's a maximum. That only can happen if it's continuous, because I can draw a non-continuous graph, okay, that has this. I'm going to draw a non-continuous graph with a critical point C, where my graph goes increasing, then decreasing, but this isn't a maximum. How do I do that? Well, I make C an asymptote. And I have it increase and then decrease. But it's not a maximum because it actually does not exist at C. Or I could have had my graph go like this. The blue graph is increasing until it gets to C, and then decreases afterwards. Does it have a maximum at this point? No. Because it hops up over here and is actually close to that point, but not equal to it. So this part here is important. That idea of continuity, super important for all of these things. Mr. LaFrance and I were talking about it yesterday, and we thought there's nothing in grades 9 through 12 pre-calculus that you ever had a requirement first before you could do something. You just did things. It's like, you should factor. Oh, wait a second. Are you allowed to factor here? Like there was never a, you can't even try factoring because the letter we're using is Q. Any questions with Q? Can't factor, even try. If you try, I'm going to take off mark. No, there was never anything like that in grades 9 through 12. But now we have requirements before we can go into the next step. And that requirement is usually continuity. Decreasing, then increasing. Increasing, then decreasing. And increasing and increasing again, that is called a stationary point of inflection. The local maximum changes from increasing to decreasing. Again, if you draw your sign diagram, super obvious to see it. Minimum changes from decreasing to increasing. Really obvious that it's going to be a minimum. Again, only works if it's continuous. Because we could draw an example or a bunch of examples where if you didn't make it continuous, it wouldn't work. So find the stationary point. Stationary point means f prime of x is equal to 0, or in this case y prime would equal 0, and show that it is a maximum using the first derivative test. So first of all, we find our derivative. We set it equal to 0, and we would know that at x equals 5/2, we have a stationary point. So stationary points are where the derivative equals 0. Critical points include stationary points, but also include where the derivative does not exist. Make our number line. Label your sign diagram number line with f prime of x to remind yourself that when you're checking whether it's positive or negative, you're plugging that into the derivative. The number one thing that's going to cause you confusion is you're on a test and you have three equations. You have the regular equation, you have your derivative equation, you have your second derivative equation. And you're like, you have to plug in two. And you're like, into which one? Okay? Because when I do it in class, I plug things into the right equation, you just nod your head. When you get to quiz or test, you have to plug it into an equation, and when you have choices of three, all of a sudden you start to second, which one should I do? So to find increasing and decreasing, I label this sign diagram with f prime to remind myself I'm plugging things into f prime, and when I plug in 0, I get positive 5. So I know this section is positive. When I plug in anything bigger than 5/2, if you're unsure, choose something huge, 1 billion. I'm a little bit unsure of my mental math. 5/2 I know is pretty small. I'm pretty sure 1 billion is bigger than that. Okay, -2 times 1 billion, -2 billion, plus 5, still negative. And we know that that part is decreasing. Any value after 5/2 will tell you that it's negative. And so we know that it is a relative maximum. Okay? It said find the point. Now we take our 5/2 and any point you would plug that back into the original equation. Because points on the graph have to satisfy the original equation. So first we were plugging values into the derivative. Then it said find the point. And now we had to plug in 5/2 into our equation. If this was non-calculator, I would have to say this would be a bit annoying. And if it was calculator, I sure hope you wouldn't do all that mental math. You would use your calculator to get that answer a lot quicker. So something to start thinking about. If I have use of my calculator, how could I do it quicker? Because you're going to be tempted when you have your calculator to do old school, like, oh, I can figure this out. That's great, I'm glad you can. But if you have a faster way with your calculator, we should use that. I was listening to a news article today on quantum computing. And, you know, computers are fast, right? Like if I had pen and paper and there was a computer right beside me and it was like, okay, we're going to race. First one to 100 decimals correct, square root of 10. Go. Computer's going to beat me. How fast do you think a computer here can do the square root of 10? Milliseconds? It's not like 100 decimals? Probably milliseconds. Okay? They're saying about these quantum computers that calculations that would take computers hundreds of thousands of years. I can't even imagine what kind of math you could ask a computer to do that its calculations would take hundreds of thousands of years. With quantum computing can now take a couple of minutes. That's crazy. There's currently problems in our world that we're like, we could solve this if we could only do these calculations, and then we'll get them done in a couple 100,000 years. Right? Now, in minutes, that's crazy. But they're a little bit unstable. So you can't have like a cell phone that's a quantum computer yet. They have to be like really, really cold in order to work. I think minus 200 Celsius about, something like that. So that probably would not feel good in your back pocket. Anyways, find the stationary point and show that it is a minimum. So, definitely continuous. 1, stationary point. Find the derivative. Set it equal to 0. Get x equals 2. It's a parabola. You know it's a minimum, but with the first derivative test, we make our number line. We plug into our derivative to see that it's negative before and positive afterwards. Since it's a parabola, I don't mind if you cheat here. Because you know this, right? It's a parabola opening up. So you could cheat and say it's going to be negative then positive without having to plug it in. However, it's not hard to plug in 0 for something less than 2 into here and see that it's negative 8. Plug in 3. Get positive 4, see that it's positive after. It's not hard. And so it has to be a relative minimum. Did it say find the point? Yes. So now we have to take that 2, plug it into the original equation, and we get 2, negative 3. Is that quicker than completing the square to find the vertex? Maybe. So some calculator stuff. You know how to find max and mins on your calculator? Right? You type it in, type in some function, and then, do we leave this? Yeah, let's leave this for tomorrow. You can write it down. I'll pause the video. I'll give you some time to start your take-home quiz.